Hi, my name is Corrado and I am a PhD student at the Cognitive Robotics Department at the Delft University of Technology. In this video, I'm going to briefly present our work titled Unbiased Active Inference for Classical Control. The starting point is introducing what active inference is in a nutshell. Active inference is a neuroscientific theory that tries to explain how action and perception might happen in our brain. The state estimation and control are achieved through the minimization of one single cost function, the free energy of the system. Most importantly, active inference allows to control systems with larger model dynamics. Active inference has been successfully applied for the control of robotic manipulators. This is me in one of our previous works, annoying this poor panda arm, which is trying to reach a goal. However, despite the success of this active inference controller, or AIC in short, there are some limitations. This is indeed another video of me in a retail store where we might want to handle delicate objects like bananas. How you can see, the AIC has quite some overshoot, and this might damage the product. The contributions of this work are twofold. We first theoretically and empirically show the limitation of the AIC in a retail scenario. Second, we formalize what we call the Unbiased Active Inference Controller, or u-AIC, to address them. To really understand the problem we're trying to solve, we need to have some background on the AIC. The starting point for AIC is the generative model. We can represent this model with a factor graph. The squares are probability distributions, while the circles are random variables. The important thing to remember here is that the goal for an active inference agent is encoded in a prior distribution P of x. I'm going to do a magic trick here and skip the derivations to obtain the free energy, but you can find them in the paper. The free energy expression here is dependent on the observations and on the belief about the states, mu. Both state estimation and control are achieved through gradient descent on the free energy. For state estimation, we obtain an expression for the beliefs update, and since f depends on the beliefs directly, we can easily compute this gradient. However, for control, we have to take partial derivatives of the free energy, since f does not explicitly depend on actions, and this is a little trickier to do. Now that we have an idea of how the AIC works, I will summarize for you the challenges we found out in our paper. First of all, in this scheme, the state estimation might be inaccurate because the goal is encoded in the prior distribution P of x. As we showed in our paper, this leads to a state estimation equation which is biased towards the goal. The belief mu indeed converges to the following expression, and here we can clearly see the dependence on the goal. The second challenge we highlight is the fact that interval control law can lead to integrator wind-up and overshoots, as we've seen earlier. The two challenges are particularly evident in case of interaction. Take for instance these two simulated reaching tasks, where during motion we have a blocking collision. Especially during collision, the state estimation is not accurate, and the belief converges somewhere in between the true state and the goal. Moreover, it is very clear that during the blocking interaction, the control input monotonically increases due to the integral action. To address these challenges, we propose a different version of active inference, the so-called unbiased active inference. Let's take the generative model we have seen before. Instead of encoding the goal in the prior distribution P of x, we augment the generative model to include a control distribution P of u given x. In this extended model, the goal enters this distribution rather than the prior. It turns out we can make the same derivations, however this time f explicitly depends also on the control actions. Then we can simply take the gradient without partial derivatives to compute the control update. The u-AIC has quite a number of benefits for classical control. First of all, the state estimation is not biased towards the goal anymore. As we show, the belief now only depends on measurements and state update, not on the goal anymore. Second, the u-AIC allows for more flexible definition of the control law. In fact, the control law converges to the function f star, which can be defined by the user. And finally, the u-AIC maintains all the benefits of the AIC, such that being adapted to unknown dynamics. Let's see now the performance of the u-AIC in a simulated scenario. This is the same scenario as before, where we want to reach the target, but we're blocked for some seconds. The u-AIC maintains correct state estimation also during the collision, and allows to safely limit the integral control action to avoid accumulating error. We also tested both the AIC and the u-AIC during reference tracking. Here we have the AIC, and as you can see, the performance for reference tracking is quite poor. This controller works quite well for point-to-point motions, but we found out that it becomes tricky to tune for proper reference tracking. In fact, a more aggressive tuning of the u-AIC would result in high overshoots in case of collision. On the other hand, the u-AIC performs quite well during reference tracking. Here we have the same sinusoidal reference, and as you can see, we obtain much better results. The state estimation is more accurate, and the controller is more easily tunable. Finally, we compare side by side the u-AIC and the u-AIC while handling delicate objects. As we've seen earlier, the u-AIC is not very gentle with our poor bananas, while the u-AIC is much more gentle and safer during interactions. So, we have seen that the u-AIC has some limitations when used for control with interaction and delicate objects in a retail scenario. These are mainly two. The state estimation can be inaccurate, and the integral control action can lead to large overshoots. On the other hand, the unbiased active inference presents accurate state estimation, less to no overshoot, and better reference tracking while maintaining the benefits of the u-AIC. Thank you.